and see you well.
Okay, that's great. So this is the first time I'm in the office now for several months, actually. So it's really great to be with everyone here today. Thank you so much for joining the OpenFOAM conference, the ninth consecutive conference that we're holding here from ESI and OpenCFD. The very first thing that I would like to do is, first of all, cancel my camera so that I can concentrate on the presentation. I'll do that right now. If you can see my screen okay, Manuela, then I'll just put that in full presentation mode. Just shout when you can see it clearly.
Yes, I can see it. And now it's in presentation mode.
Okay, that's perfect. Thanks so much, Manuela. Okay, the very first thing that I would like to do, really with a very exciting program we believe we have for you, is to express our sincere thanks to our eminent keynote speakers and also to our sponsors. So you'll be hearing from our keynotes during the course of this conference, first from Dr. Akshai Runchal this morning, and then finishing off the conference tomorrow afternoon with a keynote speech from Philippe Spallat, very eminent in turbulence. So really glad to have both these keynote speakers with us. Thank you so much. So my name is Fred Mendonça. I'm the Managing Director of OpenCFD Limited here in the UK. It's our very great pleasure to be releasing OpenFOAM for you every 6 months on a fully QA basis. I'm also the permanent chair of the OpenFOAM Governance Steering Committee. For my sins, I'm also within ESI, the director of the Technical Expert Leaders. That's leading a group of technical experts who are really looking to combine solutions from multi-physics and simulation in engineering. So many people are continually surprised by who ESI is. I'm just going to spend the next few minutes giving you a short potted history of something like now into the 5th decade of engineering applications with simulation and simulations technologies. So this year marks 47 years of existence at ESI. We are present in around 20 countries, 19 R&D centers worldwide, and employing around 1,200 employees across the globe. We have a very unique mission here, starting from 1973. We were the first ever company to be demonstrating virtual crash testing and offering that as a software offering through PanCrash, which many of you would already have heard of in 1991. The company became truly global in 92 and experienced the first initial public offering in the year 2000. Since 2000, the company has been growing essentially by acquisitions to expand the amount of offerings that we have with engineering solutions on a very wide basis for our client base, including the acquisition of the OpenCFD team, which is today releasing OpenFOAM on a 6-monthly basis. 2 years ago, we welcomed our new CEO, that's Christelle Druveret, who is maneuvering us into the next decade of successful interaction with our client base. So it's my pleasure to extend the welcome from Christelle Druveret to all of you here today. She is continuing her very strong commitment to open source and to OpenCFD in particular. The releases of OpenFOAM are fully supported by the whole organization led by Christelle Druveret. Many of you will probably already know her as one of the founding directors of the OpenFOAM Foundation. So she continues to entrust the releases of OpenFOAM on this 6-monthly basis to the team here at OpenCFD, but also to all the community contributors, that's all of you out there. ESI's mission statement, pretty much, it has been consistent over something like the 5 decades that we've been in existence. We continue to be a leading software partner in releasing software for virtual testing in engineering. We pride ourselves on a very high level of physical simulations, and now the combination of physics together to form engineering chaining solutions. The way that we do it is really from the basic structure of innovation. So we start with innovation, and you'll see that most recently what we've been able to do in entering the market with the digital twin equivalent here that we call the hybrid twin, and making this available through physical and cyber systems. That is obviously virtual engineering, but also cloud-based engineering. We do that because we know that we have great unique differentiators. The talent that we have here at ESI in terms of multiphysics is pretty unique. The uniqueness is shown in terms of chaining capabilities, combining several pieces of physics, not just for fluid flow, as you see with OpenFOAM, but in terms of structures and acoustics and structural engineering, crash engineering, electromagnetics, systems modeling, virtual reality, and several other key engineering components, which is very useful for engineering chaining. So I'm just about to give you here a few customer examples with respect to the chaining and the use of our several tools at ESI, one of which is OpenFOAM. OpenFOAM was used at Audi in the design and then the subsequent release of the e-tron SUV vehicle. So OpenCFD's tool, OpenFOAM, was used in the aerodynamic calculation of the drag and aerodynamics efficiencies. Our acoustics solvers was used for acoustics and vibroacoustics, and also in terms of VPS, the structural solver in terms of crash and testing. Our presence in the crash and testing and safety in production engineering continues with the assembly of several components in crash testing here exhibited by a demonstrator and by Nissan Motors. Our very latest offering is in multi-materials and joining assembly technology. In this, we're able now to reduce the amount of assembly time in terms of simulation from several days or weeks to even in some cases a number of hours. So this is with respect to purely virtual engineering on assembly and manufacture. We're actually very pleased in the last 12 months to be noting the impact of CFD and OpenFOAM in ventilation strategies towards high indoor air quality. And that is to maximize clean air circulation and also to minimize the risk of transmission. We've all suffered in the past 18 months from restrictions in terms of travel, restrictions in terms of office working. And here we're just about coming out of the restrictions, but with our eyes open to several things. First of all, the ability to be using software to understand what circulation of airflow really means. But the next step beyond that is to create some measures and metrics to make sure that those who are not familiar in general with fluid dynamics as part of their core activity, to be able to understand it well enough to be making decisions. So that decision making in public transport, in public services, healthcare, education is really leaving it to the experts in their fields to be making clean and clear decisions on the basis of expert metrics that we are providing for them as the experts in fluid dynamics. One thing I will ask you to watch out for in the next couple of days, this is actually on Thursday, on the 21st of October, between European time 1 and 4 o'clock, is a free workshop that we are holding on air quality lessons learned from the COVID pandemic. So this will be external presenters demonstrating how they have been able to use the CFD simulations, essentially to improve their exercising of getting back to work and minimizing risk. I mentioned decision-making. Decision-making from non-experts is ultimately going to benefit a great deal from the new form of technology which is hitting every sector of engineering at the moment. I'm headlining it with AI, artificial intelligence. Several people know it with or by different names like machine or deep learning, ROM, reduced order modeling, MOR, model order reduction. Using techniques such as proper generalized decomposition, which is a uniqueness of ESI in general, and all towards optimization. So we're very pleased during this conference to be opening up a new session on artificial intelligence, and that's going to happen this afternoon, CE time from 3:30. So please watch out for the presentations there. Essentially, it means to be able to exploit this kind of decision-making from artificial intelligence or machine learning. What we need to do with our simulations is exploit them from a solid basis of solutions and software solutions which are robust, repeatable, accurate, and reliable. So let me finish the ESI spectrum here just by renewing our commitment, not just to OpenFOAM, but to the community in the wider general scope. So our corporate resolution to really all sectors, that is to our employees and customers, to the general community, and to the well-being of the environment, is that we'll continue to focus our engineering solutions for corporate social responsibility. Okay, as I've mentioned 5 decades already, this is my own brief potted history of a little bit of CFD history over the past 5 decades. My own history goes back probably to around 1983, 84, so that's only 3 to 4 decades. And you'll see at the bottom right of the picture that I've introduced there a picture of the front cover of a volume which was compiled by Dr. Akshai Runchal, entitled 50 Years of CFD in Engineering Sciences. My own potted history is making a strong acknowledgement of 2 characters in CFD that have been prominent over these 50 years. That's Anthony Jameson at the top of the picture, and Brian Spaulding, the bottom picture. So I'm now going to pass on to the person who has compiled that 50 years of CFD in engineering science, and that is Dr. Akshai Runchal. We are really extremely pleased to welcome Dr. Runchal to give this keynote talk. And with that, I'm going to pass on to Akshai. Manuela, I think at this point, although Akshai is live online, we have a pre-recorded presentation that you will now put online. Can I pass back on to you, Manuela?
So you want me to play the recording?
Yes, if that's okay, that'd be great. Thank you so much.
Fred, give me a second.
Good afternoon. My name is Akshai Runchal. It's a pleasure and a privilege for me to be speaking at this event, where my former professor. Good afternoon. My name is Akshai Runchal. It's a pleasure and a privilege for me to be speaking at this venue, where my former professor and mentor, Brian Spaulding, gave his last professional talk in 2016. I hope I can do justice to his memory and to his training. The topic of my talk today is 50 years of CFD in engineering sciences. This will be a personal perspective. I was fortunate enough to be present at the birth of this engineering discipline and have spent all my life marveling at its intricacies and its promise. It has been fun, and I hope to convey that to you. Here is a summary of my talk. What is CFD? How did we get here? What can we do with it? And most important, where are we going next? So what is CFD? As Spaulding was very fond of saying, we inhabit fluids and fluids inhabit us. We are surrounded by air. 2/3 of Earth's surface on which we live is water, and 2/3 of human body is fluid. CFD predicts the behavior of fluids, plastics, and deforming solids. It solves the most complex and interesting problems we face. It's challenging, it's fun. So let's look at the integral approach to the CFD that leads to the general balance equation. The balance of a property phi in any arbitrary finite volume is given by rate of accumulation is equal to the net influx through the surface and the net rate of generation. So here is the arbitrary value V with a normal surface normal N. So that is the equation that results. The flux is basically the amount transported from the surface through movement velocity multiplied by the normal area. And of course, the accumulation is simply what accumulates inside the volume, which is the rate of change of that property. And this is the generation terms. Actually, CFD is very simple. Don't be overwhelmed by any complex equations that you're shown in your regular CFD courses. Your teachers have to earn their salary, so they make it complex. It's basically the change in your bank balance is equal to net money in plus net rate of interest and bank fees. CFD is no different. Always think physics. I tell my students, think physics, not math. If you can manage a bank account, you can do CFD. So if we take this equation and use the Gauss theorem, and as we shrink the control volume smaller, then from theoretical consideration, we can say that the integrals drop out and you have this differential equation, which is basically just the flux times the generation. The Imperial College approach was to generalize this equation, what we call the general transport equation. And basically, it's the same terms expressed and generalized in a different way, where there is a storage of a property, phi. This is kind of an accumulation or storage coefficient, such as specific heat for thermal energy. This is advection or convection, which is the velocity times the property multiplied by some specific property, such as density. And this is the diffusion of that property due to molecular diffusion, right, at the inherent Brownian motion that occurs at the molecular level, because we're taking a continuum approach. And then finally, we have the sources and the sinks. So basically, this equation expresses the balance of any property that can move in a continuum approach. Could be fluid, heat, mass, electrons, cars, humans, fishes, anything in large enough numbers to be considered a continuum. Why do it? What's the motivation? The physical world is usually divided into solids and fluids. In reality, there are no solids. It's only a question of temperature and pressure. Solids are essentially fluids at rest. Everything moves one way or another. There's a continuous transition of matter between solids, plastics, liquids, gases, and plasma. So CFD, in a broader sense, is the science of things that moves. Okay, could be fluid, could be plastic, could be anything that moves, could be fishes. So almost every human endeavor involves fluids. Okay, remember, man inhabits fluids and fluids inhabit man. So we need CFD to understand our physical and biological world. That's why we do it. Now, what can be done with it? To me, it's more a question of what can't be done. There's hardly anything that can't be done. Practically everything moves. It's the science of motion. CFD applications span human existence, industry, environment, human body, biosphere, from deep in the earth to the outer reaches of the star. There are infinite applications. CFD tools today are critical to aerospace, energy, transport, national security, engineering design, manufacturing, food, chemical processing, consumer electronics, consumer goods, life sciences, pharmaceuticals, environment, disaster management, earth and geological sciences, astronomy and outer space, and now entertainment, increasing role of CFD in virtual reality, animation, and film industry. So let's come to a personal perspective, a bit of a subjective history. I grew up in the remote hills of the Himalayas. You see my hometown there. was born somewhere in just next to this dish on this side here. I never dreamt of participating in the birth of a new branch of engineering sciences. I thought I'll grow some sheep and have a herd of sheep, and that was the main occupation of the people around there. I never thought that this remote hamlet of 3 families, we were 6 adults and 11 children, will be once known throughout the world. But I witnessed the emergence of CFD at Imperial College. I was a part of it. McLeodganj became the home to Dalai Lama, my birthplace, a symbol of rejuvenation of Buddhism and a cause célèbre for human rights. And today it plays a prominent place on the political maps of India, China, and the US. I'm indeed a lucky man. I was at the right place at the right time. Like any science, like Newton said, I stand on the shoulder of giants, therefore I can see farther. So the early mathematician, starting with the 16th century, developed the tools that would later form the foundation of CFD. These included finite difference method, numerical analysis, matrix theory, Gauss theorem, minimization principle, the Hamiltonian, the variational methods. And then more recently, many developments have happened. 2 memorable ones in the last century were that of Richardson and Courant, Fredericks, and Levy, who introduced seminal contribution to the theory of numerical methods like relaxation methods. And then Courant went on to contribute by introducing the concept of upwind differences, which became central to high-speed flows. Amazingly, there was CFD before electronic computers. Electronic computer didn't come on the scene till late 1950s. But in 1933, Thom developed a finite difference solution for flow past a cylinder. He used stream function of vorticity with a central finite differences and an iterative method, and was able to obtain a stable solution for Reynolds number of 50. How did he do it? He was very innovative. He collected what he calls urchins, street children, and he paid them certain amount of money for each correct calculation, addition, multiplication, and subtraction. So that's what it was. So once again, CFD is very simple. If the street children could do it, surely anybody can do it. Southwell used the relaxation method for elliptical problems and made some innovative contributions. And then with Allen, he went on and introduced the concept of conformal transformations, which could map infinite spaces into finite computational domains. Apple, Kawaguchi, Simony were some of the other names who made early contributions before computers became very powerful. But the actual birth of CFD can be attributed to 2 brilliant scientists. Frank Harlow at Los Alamos on the left, starting in the late 1950s. IBM, Los Alamos got its first IBM 701 in 1953. Brian Spalding at Imperial College, he started in the mid-1960s. Imperial College saw its computer IBM 7090 in 1962. Both worked independently without knowing much about each other's work till it was almost done. And there was no internet in those days. Air travel and phone calls were very expensive. To my knowledge, the two never met. Our group at Imperial College first knew in depth about this work when Tony Hurd from Los Alamos visited us in the 1970s. But it was Spalding who made CFD a common and popular tool for engineers. Frank Harlow was at a national lab. He was part of the Manhattan Project, a very secret process, a secret project. He was not interested in publicizing his work or in making his software and technology available outside. And otherwise, he was a physicist by training, and he did not have any interest in engineering application other than those related to his projects. So the CFD started emerging at Imperial College in the 1960s. But one of the reasons the CFD Imperial College made a significant dent or significant impact was because the prologue was already set by developments that Spalding had undertaken starting in the late 40s. Okay. In 1948 to 60, Spalding developed a common format for fluid flow, heat transfer, and mass transfer. Before that, the normal thinking was that people thought either in terms of flow or heat transfer or mass transfer. But Spalding realized and emphasized that these are essentially very similar processes. Basically, the mathematics that underlies them is very similar. He then went on to develop a unified theory of boundary layers called Universal Theory of Boundary Layers, Jets and Wakes, on which he worked till the mid-1960s when we started switching to the computer software. The other very important component was the in-depth survey of experimental data that led to universal empirical constants, which were needed to account for turbulence processes. Okay, before that time, everybody had their own favorable value of the turbulence constant. Okay? And he also did some innovative contribution in theoretical experimental combustion work, including evaporative burning of droplets, and these led to the B factor or the Spalding number for mass transfer. So when it came to practical application of CFD, these would prove very crucial. And these developments came to be known as the IC Imperial College approach, which was later called the finite volume method. So the landmarks in this period were, first was Suhas Patankar built an integral profile for boundary layer codes. Before that, people employed a specific profile for each application for self-similar flows, such as boundary layers. Spalding hypothesized or proposed that we can create any profile by a set of linear or polynomial profiles. Any profile can be made up with that, right? Which is true to any accuracy. So he asked Suhas Patankar to employ this concept and generalize the profile method, and that known to be came as the profile method. At the same time, I had joined Imperial College a few months later, and so had Mika Wolfstein. So Spalding asked me to use the stream function vorticity method and the finite difference method to compute separated flows, and Mika Wolfstein to do the same for the impinging jets. He knew that most engineering problems were not boundary layer. Boundary layer played a role, but actual problems had more complex flows, and two important class of flows were the separated flows and the impinging jets. So if you could cover all this with his universal theory, then the problem would be that we would have a very general methodology. So myself and Wolfstein combined our work, and we developed the first general purpose finite volume code for two-dimensional high Reynolds number flows. That was in 1966. And that went on to be the basis of the first book published on CFD called the Imperial College Finite Volume Approach by Academic Press. Patankar and Spalding then made a very important contribution in 1972 and developed a three-dimensional velocity pressure-based code, which incorporated the simple methodology, okay, that had components that were developed at Los Alamos. So this basically generalized and revolutionized the practice of CFD. By the start of 1969, Spalding had realized the importance and the commercial potential of the developments. In 1969, he organized a post-experience course at Imperial College, which targeted both academic and industrial communities. He also incorporated the first commercial company in CFD called CHAM, and then also published the first book on CFD, Heat and Mass Transfer and Recirculating Flows by Academic Press. This book contained the full computer code for 2D Navier-Stokes equations called ANSWER, which was freely distributed. We had not heard of the intellectual property in those days. All the codes were published. Another interesting part was that Spalding had a strict rule that all joint publications carry the names in alphabetic order. That's how the authors are listed in our book. David Gosman actually compiled and edited the individual contribution from Spalding, myself, and Wolfstein. And Sam Poon was the person who took over the answer code and its further development, because both Mika Wolfstein and I were leaving to take up appointments abroad. Another interesting thing was that there was finite element methods were getting to be used for structures originally and then for fluids. So the Imperial College group interacted with both Argyris and Zienkiewicz, two of the pioneers of the finite element method. Argyris mostly stuck to the solids part, structure part, but Zienkiewicz was the first one to try and extend it to the fluids part. So the merits of both were very hot topics. We met with both of them, with especially Argyris many times, because he was at Imperial College. And Zienkiewicz was not very far. He was at Swansea. So our assessment at that time was that finite element was unsuitable for high Reynolds number flows. At that time, it didn't have a clear theoretical basis, and Hamiltonian or the minimum energy does not exist for nonlinear systems, which was the basis for minimizing the overall global integral. Later on, of course, they went on for the variational methods where you don't need a minimization principle. The other disadvantage in our view was that finite element method uses global error minimization. Local mass balance, on the other hand, can be very important for highly nonlinear systems, such as with chemical reactions. A small change in temperature can lead to a fourth order change in, say, chemical reaction rate. So we were dealing with many of such problems, so we decided that we were not going to use finite element method. Of course, over the years, both have appropriated, borrowed, or stolen from each other. Now the finite elements do upwinding, and we generalize and use general geometries. So the differences are more semantics than substance. But the fact is, for a number of reasons, most commercial codes still use finite volume method, and certainly most codes that deal with high nonlinearities, such as combustion or very fast transient changes, they use usually finite volume method. CFD-COM name was not coined by either Harlow or Spalding. Actually, it was first used by Pat Roche in his famous book called Computational Fluid Dynamics. The IC approach led to the development of CFD as an engineering tool. Application of CFD, a problem of interest to engineers in the general community, started with Imperial College. There was a unified framework of flow, heat, and mass transfer. So you didn't have to solve just for three different equations. You solved basically one general transport equation for all of them. And the other important component was that the focus was on physics rather than mathematics. This made a big difference. We dealt with engineering concepts such as volumes, masses, fluxes, and things of that nature. The Imperial College group did not understand all the theoretical aspects, but such as for turbulence, but we knew enough to get the job done. So the philosophy that Brian Spalding had and permeated our thinking was the proof of the pudding is in eating it. Turbulence is a good example. Okay? If we can solve an engineer's problem to enough accuracy to enable his job, that is good enough theory for us. So as I said, that most of the commercial codes trace their origin to CFD, and examples are OpenFOAM, ANSYS, Star CD, Answer, ACE, and there's a long list. Let's look at the present. CFD today is one of the most powerful tools in every field of human endeavor. It's pervasive in our industry, economy, environment, and our very existence. I already gave you a long list of fields where it's playing a crucial role. You name it, and there's perhaps a CFD study in that field. The list of what can't be done will be very short. I will not dwell much on this topic. Every day, a new field seems to open up for CFD. I'm just going to show you a few illustrated examples just to illustrate the width and the breadth of application. So let's take the field of environment and disaster management. Here is a hypothetical tsunami that's going to tsunami out what are the maximum elevations of water study, or allows us to do that, which of course will not be possible in reality. Okay, so we cannot actually study tsunamis in advance. We can only do it in hindsight, which can be disastrous. So here is another example of Sumatra tsunami. And we were asked by the Bhabha Atomic Energy to find out the impact of the Sumatra-like tsunami. And we recreated it at levels along the Indian coast. And there is some papers which define how that, and it was a very good replacement and of nuclear power plants. Now we come, and here was a study in France of the dispersion of sewage of the Dieppe harbor, and sewage discharge can be simulated, and it moves with the ocean current phase. You can see the cross from where they are impacted. So the impact of these can be defined in this manner. Another example is from human body and pharmaceuticals. And here, for example, there is a blood-brain barrier which doesn't let certain or many chemicals get to the brain from our body. So sometimes it's necessary into the brain. And so the question is how fast they diffuse, how far they go, what are the concentrations. So this was a study that we had, a cooperative study with the University of Virginia, where we did, the poor rat, of course, was chopped up and sliced and then compared. Next, we look at the airborne transmission, the impact of ventilation, a very topical subject today, and enables you to figure out what happens during ventilation, how far it can travel. And one of the net results of such studies, it was recognized that the common instruction of staying 6 feet apart makes some sense, but only in instances where there is no transmission due to ventilation and other things, and ventilation can play a very strong role. There are some engineering applications here. I think the most famous ones are those of the car, both the exterior of the car and the interior of the car, where this particular one shows the skin temperature distribution for comfort inside the vehicle. So today, no car is designed and no aircraft is designed without, no metal is cut without CFD study being done first. This is another topical case of the wind turbine, which wind generation is a big factor. And here is a study of a wind and simulation of a wind that will allow us to decide what should be the spacing between the wind turbines and how far, and how to space them so the maximum energy can be extracted from the wind. CFD is used in astronomy. Here is a comparison between the numerical simulation and M81, the actual M81. So CFD is a well-studied case of spiral stellar potential-driven shock and star formation, plays a big role. Electronics, you are all familiar with that. The gas turbine engine, which drives all our aircraft and much of our energy on the ground also, is one of the most complex machines. And as I said before, no gas turbine is designed today without CFD. Now let's look at the future. So the first thing is preparing for the future. There are a number of challenges on the CFD horizon. So what are these? CFD today is a combination of science, such as Navier-Stokes, Boltzmann, thermodynamics, which have well-defined physics and accepted mathematical basis. Then there is a lot of art that goes into it in designing an efficient system with computer resources, which are always limited. So what is the best we can do with it? But most important, there's a lot of guesswork. Okay, if you go beyond the regular laminar flow, you'll find that we don't understand turbulence. So many aspects of real fluids and their behavior are poorly understood and have very poor scientific basis. They are only hypotheses or empirical data. Empirical data are usually very limited, only a few specific subsets. So rest of the time, we have to use a hypothesis, what we call a model, a turbulence model, and you know how many there are. I think I can count 100 turbulence models. So that is what is our best guess. Lack of knowledge, poorly understood physics and chemistry. Reaction mechanism. A simple reaction such as hydrogen and oxygen can be defined as a one-step reaction. If you just want to know what the power produced, energy produced is, you can say H2 plus half O2 leads to H2O and so much of energy. But if you want to understand the mechanics, different temperatures and pressures, what is the impact in terms of intermediate species, you can go to a 50-step reaction, or maybe I've seen 200-step reactions. It depends on the operating condition, what is their objective, okay? So complex hydrocarbons are mainstay of energy. The fact is that nobody fully knows the reaction rates, even the fluid properties for actual operating conditions. For example, what is the physics and chemistry of blood and cerebrospinal fluids? Is it Newtonian? Is it non-Newtonian? Is it particulate? Is it non-particulate? There's all kind of visualization, all kind of stipulations which are specific and can lead to adequate results, but we don't fully understand it. And then we have poorly understood mechanisms and processes. We don't understand fully the interaction between electrical, magnetic, and chemical processes. How does a molten rock or metal behave at high temperatures and pressures? How does the liver manufacture all those chemicals? How does the blood-brain barrier work? So this is our lack of knowledge. The other challenge is uncertainty quantification. There are two types of uncertainties. The lack of knowledge that I talked about, we call it epistemic uncertainty. Most practical flows are turbulent. Turbulence chemistry interaction is very important in energy generation. There are too many models, each with limited applicability. Other uncertain physical inputs that we require in actuality, such as diffusivity, reaction rate, is just not there. The second type of uncertainty is aleatoric uncertainty. Here, something that we know varies randomly or stochastic. For example, take the case of trying to do a simulation of an ocean or an atmosphere. Well, we don't know the initial or boundary condition. What we need are the initial or boundary conditions at a given time at a specific time, at a specific location, all the locations. We don't have those. Physically impossible. Not only that, we do not sometimes understand the domain of influence. Jet stream goes around the world. So if you're doing a weather simulation where jet stream is important, your domain of influence is the whole world and perhaps going 50 kilometers up. Then there are situations where there are multiple uncertain inputs. Okay, that happens quite often. The flow that occurs underground, for example, we don't know the porosities, we don't know the actual situation, actual topography, and we don't know, for example, the hydraulic conductivities or whatever other inputs we need. And there are multiple, all of them, we don't know the initial conditions, boundary conditions, all of them are asserted together. So how do we make scenarios which give us or cover the broad range? That becomes our problem. Another big challenge today is multiple coupled phenomena. Multiphysics has become I would say, the status of today. Practically every fluid problem that we're studying has some multi-physics component to it. Whether that is fluid structure interaction, or whether that's, for example, take combustion, there is fluids, heat transfer, mass transfer, and chemical reactions and all those occurring. Take the electromagnetic influences, Navier-Stokes plus Maxwell plus thermal equations. So we solve a whole combination of them. That makes the problem very complex. Multi-phase, we don't understand, poorly understood today. Yet we need to deal increasingly with multi-phase. Many of the problems that we face practically involve multi-phase. Multi-fluid flow, for example, there are situations, let's take the groundwater as one example, where there's water, air, and there may be immiscible oil if we not study pollution in the groundwater. Then could be multi-scale, non-continuum or coupled discrete and continuum problems. Navier-Stokes and Boltzmann, both may be involved in certain situations. We could go to nanoscale to macro scale applications today for practical purposes. Similarly, we could be coupling the outer space and the inner space, the human body, where we're studying certain environmental problems. The other very complex phenomena that we still don't have a good handle on is what we call the integral differential processes. What happens is they make the problem global. Thermal radiation, aerosols, soot, sprays, particulates. These are challenges that we have not successfully solved today. 4D working domain changes in space and time. For example, folding and flapping wings of birds and aircrafts. Heart veins dilating and pulsating. Simulation over disparate time and space scales from meters to thousands of meters. Air pollution for a building can be impacted by local flows at the level of kilometers and global air flows at the level of hundreds of kilometers. Then look at the processes which occur at disparate scales. When you're dealing with flow and combustion, the combustion occurs in femtoseconds or femtoseconds to seconds. The time scale from flow could be seconds to minutes. How do we couple them? Fluid structure interaction. Information speed for structures is sonic. That for fluids is based on the velocity, a low Mach number. If you couple them, what time scale do we use? What time step do we use? Then there are challenges CFD algorithms. There is still no satisfactory method to deal with convection term after 50 years of CFD. Flow regime changes from elliptic to parabolic to hyperbolic because of interaction of convection and diffusion terms. Diffusion is a second order linear process. Convection is first order, but it's a non-linear process. So dealing with both, when both are important, there creates a problem. There is no robust and accurate scheme when both are significant. I think again, like turbulence, there may be hundreds of schemes, none fully robust or accurate. And here's an opportunity for you young people who want to make their name and their career if you design a scheme that works robustly and accurately throughout the regime. Other challenge is related to resources, matrix solvers. Governing equations today admit multiple solutions, nonlinear. Turbulence is a good example. Okay, but computational methods linearize nonlinear equations. Matrix solvers can only solve linearized equations. And then all computational methods lead to large matrices of unknowns, millions of unknowns. Maybe somebody is doing with billions of unknowns. There's no satisfactory matrix solvers for such applications. It's often a trial and error and grunt work. So we need robust, accurate economic solvers that produce solutions when it exists. And then what do we still do with the nonlinear part of it? Computer architecture is evolving fast today, with parallel and cloud computing becoming the norm. CFD methods have not evolved to optimize their use. Their origin was at the time, for example, if you look at the history of the dominant computer codes today, their methodology you'll find is not fully suited for parallel and cloud computing. Okay, it's hard to fully and efficiently utilize computer resources. They do not scale linearly with processors. Communication time required at some stage can exceed computing time with the method we are using because switches are slower than CPUs and GPUs of the processors. So we need better management methods for cloud and parallel computing, and we need better computational method to optimize use of evolving architecture. One challenge is decision-making. CFD plays a crucial role in many aspects of human, social, and economic endeavors. However, the software available today is neither robust nor accurate. No code vendor today will undertake liability if real system does not follow their CFD predictions. It's still a forte of CFD experts, not a tool for average design engineer. It's a tool that needs a lot of training. Decision makers require input that can be easily understood. So we need better methods to present input to decision makers, and we need robust codes that predict results with acceptable uncertainty bands for design purposes. So let's look at the future, the last part of my talk. The future of CFD can be deduced from what happened to the car. In its early stages, it was the engine that determined the car you drove. I grew up and I knew what the engine of a car looked like. Now it is the interface and the objective that people look at. You buy a car that meets your objective. Well, whether you're a commuter or a race driver, you'll figure out which car is best for you. And then you look at the interface and you look at the comfort, you look at the gas mileage. When was the last time you asked the salesperson as to what type of engine and with how many cylinders, how much displacement, things of that nature? We don't do that anymore. So what has happened is that the engine, which really is crucial to the car, is actually become invisible to the user. So something similar would happen to CFD. There will be special purpose applications called apps or tools, and CFD codes as we know them today will disappear, or they'll be buried inside apps. Because today, these codes are too cumbersome to use. They require long training period. They're very resource intensive, and there's no checks and balances for reality. There's poor overall reliability for critical applications today. So this hopefully would change. So hopefully we'll have better use of computer resources, architecture, algorithm solvers. We also hopefully will have better science, less guesswork. I hope we will have better models such as for turbulence or physical processes. Maybe we would go more and more to direct solution, direct DNS. And we would hopefully develop better methods for dealing with stochastic phenomena. But the big impact that will also occur is due to the machine learning and artificial intelligence which will incorporate CFD knowledge. We will have digital twins, we'll have physics-informed neural networks, and we'll have engineering virtual reality for decision-making and for showing the results and understanding the results. And hopefully, this will come with built-in voice and interactive commands and engineering Siri, for example. In summary, CFD of the future will be special purpose apps for an engineer that he can interact with to meet a specific design objective, and not a general purpose tool that she spends 6 months to learn. Here's an example of the virtual reality that we used some time ago, and where we studied the tsunami at Cannes, a hypothetical tsunami, and we actually took the things and everything else. So the question was, what would happen in the tsunami, which parts would flood and which part we should prepare. Created this reality and then superimposed on that the results of the okay. Let's come to machine learning, which would revolutionize CFD in the coming years. There's basically neural networks. That's what machine learning is. And there are deep neural networks, such as in any translation or Siri or any of these voice commands that you see today on your phones. There's deep neural networks with multiple layers which are built into it. Each layer feeds to the next one to give a final result, which hopefully is understandable. So it's been successfully applied in many fields: image processing, natural language, speech recognition, and it can also deal with high nonlinear problems. So machine learning can also be used to augment lack of knowledge of a process or phenomena. For example, we can use machine learning to figure out what terms need to be added to the RANS model for a specific application. Now, physics-informed neural networks are basically neural networks in which Navier-Stokes equations are embedded. So you take the regular neural network, it has the input, you output that come, you feed into Navier-Stokes equation and see if the equations are satisfied. If the equations are not satisfied, you go back, refine your neural network, train it again till that happens, and finally what you have is a physics-informed neural network. So the future would be machine learning, surrogate models, and digital twins. It improves modeling effectiveness. For example, we can understand novel constitutive laws such as turbulence, multi-phase flows, and combustion, where we have a significant lack of knowledge today. The training data for this can come from high fidelity CFD, from experiments, and also from real-time data. So PIN is a very good vehicle for developing surrogate models and digital twins. It basically creates a fast and accurate representation of physical system. So a digital twin is a digital representation of a device or a process which gives you up-to-date real-time representation from a data-driven model that has been enhanced with Internet of Things, PIN, sensors, and everything that goes into it. So a specific situation is shown here. This is a digital twin which feeds from the Internet of Things, and there's your logic module, your PIN modules, here's the cloud computing, sensors, networks, electronics, and somewhere buried in this one is the Navier-Stokes equation. So a digital twin is a comprehensive model of a complex system which will eventually produce a tabulated or analytical analog of the device or process. Let's take an example. An automotive cooling system contains a number of components, including a pump. Okay, so here is the complex system. Okay, the objective is to design the cooling system, not the pump. Okay, pump is bought from some manufacturer. Now, to do the multi-phase CFD of the pump is very expensive. So if you design this cooling system, you'll find you spend all the time simulating the embedded pump, because pump uses sliding meshes and multiple rotating frames of reference. There's two-phase flow with air bubbles and liquids. Large bubbles break up and they are expensive to capture. The breaking up or coalescing of bubbles is very expensive to capture. So we cannot afford to embed it in global CFD. So the solution is basically to replace the pump in the global CFD with a digital twin, which basically just predicts its behavior and gives you the values that are needed for a certain input. So here is the two-phase flow through a pump. So number of simulations with the experimental data to understand what's going on for a given input. So we generate that training data. Output is as a function of these various inputs. So pump is then replaced by a digital twin. And then we can use to improve it with empirical data. So basically, here is the summary of a digital twin. Perform CFD simulations for the component of interest. Call neural networks from the CFD solver. Combine with empirical data if available. Develop a digital twin. Then remove part of the mesh representing the component from the global CFD model and replace it with a twin. So now you have accuracy and speed up. So more demand will be placed on CFD analysts to simulate design conditions, simulate off-design condition, anomaly detection, different failure modes. Multi-physics CFD will become the norm. CFD plus structures, plus electronics, plus vibration, acoustic systems. People will be combining all kinds of things. And the future norm for high fidelity CFD simulation design processes will combine it with digital and surrogate models. So, as I said, the future of CFD modeling is special purpose apps and tools with CFD engines buried underneath. This will happen along with physics-informed neural networks and with artificial intelligence and deep learning, digital twins, and of course, everything will view the results in a virtual reality, what I call engineering virtual reality. Thank you very much, and I appreciate any.
That presentation seemed to cut off just a little bit prematurely. Apologies for that. Dr. Runchal, can I ask you to come back onto the stage now? We'll have a question and answer session for the next few minutes. If you wouldn't mind, we can probably answer those live. So Akshai, if you can hear me, please rejoin the stage. That'd be great.
So Akshai, just click the share microphone and camera button on the top right. So Akshai, if you can hear us, just click the share microphone and camera button. It's on the top right, and then you are on stage and can talk to Fred. Ah, here he is. Oh, he was. Please try again. Yes. Okay, we can see you. Akshay, can you hear us?
Yes.
Okay, so Fred.
Yes.
That's wonderful.
Can you hear me?
We
Yes.
can indeed. We can indeed. Thanks so much, Dr. Runchal. Thanks, Akshai. So that was a great presentation. It's really humbling to see what an enormous time that you've had and shared in the times of origins of CFD in general. That insight is absolutely invaluable, and thank you so much for sharing that with us. We have a couple of questions. I'm actually just going to share my screen, hopefully that everybody can see here now. On the Hopin platform, you'll see that there is a Q&A session or a panel here. Please feel free to do one of the following. Either just type your question in this particular area here, or as we've seen from Holger Marshall, you've not just typed your question. That's great. Thank you for that. Holger, if you'd like to come on screen, I can just let you ask the question directly to Akshai. Otherwise, I can just enunciate your question. Okay, here it goes. So Akshai, Dr. Holger Marshall is asking the following. He's enjoyed immensely your keynote. On the future of CFD technologies, could you please comment on your views on higher order methods, meshless methods and lattice Boltzmann methods?
Okay. Let's take in series I think the higher order methods may become more, how should I say, more prominent in certain fields, but I see the machine learning basically taking care of most of the, how should I say, computational related. As we build databases and we begin and learn to mine them, I think the issue of higher orders or the order will not be that important, in my opinion. Right now, I know the higher order methods are very important because we're doing a lot of LES or DNS and we have limited resources. But think of it this way, as the resources are going to increase, and my feeling is we need, it will not be that critical. We could throw more computer power at it. But I think a niche area would perhaps stay. When it comes to the meshless, again, I see the machine learning kind of taking care of meshless. Essentially, a neural network is a meshless method by default. Neural networks are nothing but random points in space, and you could train each of those to interact with each other based upon the basic physics. So the physics-informed neural networks are essentially meshless. So I do think that the some of the techniques which are being explored now, basically scatter points, and there's different versions of that. SPH is one, and you know, I mean, there's a whole bunch I can't name. But my feeling is that neural networks would again play a key role in making the meshless inherent. So the third part of your question was, sorry, what was the third part?
The third part of the question was different sorts of methods like lattice Boltzmann.
Lattice Boltzmann. Yes. I do see lattice Boltzmann playing a very important role in certain in certain applications. But I think there are, as multi-physics becomes more the norm, either lattice Boltzmann would evolve like finite elements evolved to learn how to deal with these additional complexities. But I think there are inherent limitations currently in the lattice Boltzmann, which make it very good for certain applications, but not extendable for very complex cases. I don't think, maybe I'm wrong, I may not be up to date, but I don't think I've seen a very good lattice Boltzmann application, let's say for a gas turbine so far, because the complexities that are inherent in such a system. But maybe I'm wrong there.
And thank you for that considered answer. Yeah, I think related to that question is the following. I mean, you've seen over the past 50 years and more, the fact from the origins that finite volume has become the leading methodology for CFD over the past 50 years. Now, from your presentation, the perspective towards multi-physics, I'm wondering whether there could be a resurgence in terms of combined methodologies of, for example, finite element or different combinations of methodologies to solve the multi-physics problems. What would be your thoughts on that?
Yes, I think it will have to be. Um, I give people this example. Many of us use Microsoft Word, for example. I grew up from the days when when the editors were very small. They were just editors, let you type and something on the computer. And people think of Microsoft Word as a Microsoft Word, but actually it's not. Microsoft Word is perhaps a combination of, I don't know how many, I haven't followed lately, but I'm sure it's more than 100 programs. You don't see them. I mean, spell checker has nothing to do with Microsoft. Um, with number counting, how many words you have, how many spaces you have, things of that nature, formatting. So there's all these things going on, but we don't see that, right? So my feeling is that the future apps, as I call them, or future software, would basically be an interface like that of a car, and you would be able to change the engine in it if you like you can have the same body and different engines. So my feeling is that, for example, it's very hard to do even today a very fast evolving transient in a slow moving fluid of a structure, because the time scale would be so different. You'll waste much of the time on the fluid doing a small time scale, which you don't really need. So it'll be much better to have a better merger of the two. Of course, Spalding was a great proponent of using finite volumes for structures also. But I think what would happen in the future is that you would have an interface to solve an engineering problem. There'll be different components. There'll be uh, targeted software that solves each of those components and brings the system together.
Okay, interesting. Thanks for that answer. That sounds a little bit like horses for courses. So you choose your solution methodology on the basis of the problem that it solves in the most efficient way, and hide everything under a hood, I guess. Which
Yeah,
leads
or
quite.
the software, or the
What?
software might. I mean, the software might decide. For example, I can write a code today which can say this component is let's say hypersonic, and I can get away with the characteristic method and switch for that part of the algorithm to the that part of the field to a hypersonic method, and keep my my more complex method somewhere away. So I think the software would become perhaps intelligent enough, because it'll be too hard to do it manually, my feeling is. So you'll have to have some automated system that decides that it's better to use this part for this part of the flow, and this for I think one good example I can give you today, even in the software, is that of when you have interact with the atmosphere. There are two different cores that are interacting very well with each other in terms of computing, because the time scales and the physics is very different between the two, but the user doesn't see them. So that's where I think it's.
Got you, and thank you for that. It kind of leads on to to the next question. Thanks to Boris Bisha from Turkish Aerospace, who's asking the following: how do you see the future of open CFD tools? I kind of interpret that as being open source CFD tools, or whatever codes which are generally open in source form to the open public to develop. Um, I know you have exposure to OpenFOAM. You very kindly also accepted this talk, this presentation as a keynote. So with open source like OpenFOAM and other open source, do you see a strong future for open source tools in this sector?
Yes, a very strong feature. I mean, we are, among other things, though I'm a professor, we do have a commercial company, and we have our own software answer that we recommend and use for certain applications. But we use OpenFOAM, we use Fluent, we use, and I'm sure ESI has a number of software codes, and then use OpenFOAM too. I think open software has would be the prevalent CFD for the general research and development. That's where I think it will be. Um, I don't want to kind of make it, how should I say, Wikipedia as the as the example, because it's not always reliable. I hope open sources would be more reliable. The situation would be that I think there would be Wikipedia, but if you really want some reliable medical info, then you can't rely on Wikipedia. You would go to a more, how should I say, credible source. Be specialized niche applications where there would be software which either incorporates OpenFOAM or incorporates a different methodology that solves that particular problem. I think that is where the future of the commercial CFD would be. But I think the non-commercial CFD research development, I think open source would be the norm. I mean, just look
Thank
at
you for those.
publishing today. I mean, if we take the example of the publishing, you see how important the open publishing formats have become compared to the closed publishing formats, which were controlled by a few companies. Now, many of the groundbreaking research today is being published on the open format platforms. So I think open source would be the way to go for future research in CFD.
Thank you for that answer. That's really well considered. Just in the interest of time, Akshai, I have one more question, if you don't mind. This is really on the basis of what would be your recommendation to young engineers? Probably 100 or more are attending this talk of yours. Listening to you, what would be your recommendation to them? Your hopes for CFD, let's say, for the next decade or two? Would you like to make a brief comment on that? Just to give us some insight into your hopes and possibly even fears.
Well, my first advice to all of them is that if you don't enjoy doing CFD, find something else to do. I have thoroughly enjoyed and I strongly believe that you should spend your time enjoying what you love rather than enjoying what you have to do. If you really love it, then my advice to you is find the niche where your interest is. Many people's niche, each would have their own niche. For example, there are so many open challenges in CFD today. I think I listed I thought I was being comprehensive, but I realized I'm not. I mean, there are so many open challenges. Look at one of those, and you have the next 20, 30 years, I hope, to make a dent in those areas. Uncertainty is a huge issue. Dealing with different regimes of the flow is a huge issue. Multiphysics and bringing, let's say, fluid structure interaction is a big issue. I mean, there are so many challenges. I would think that pick a challenge that suits your qualifications. If you're a mathematician, for example, there are a lot of challenges related to mathematics. Better solution methods, better matrix solvers, better minimizations, better robustness, how do we figure out if a code is really producing results that you can trust? Nobody, like a very close friend of mine who works at GE made a very close comments. Hey, I'll design this engine with CFD, but I won't fly on it unless I really test it. So that is where CFD is. Nobody can believe or give guarantee that the results coming from CFD are robust and good and reliable, or what is the uncertainty. So my feeling is that look at your capabilities and figure out a niche area.
It's a very sobering thought and a good perspective on checking what you do. Yeah, absolutely. We've just got probably time for one final question here. So it's from Dr. Muni Rajulu. So he says, Dr. Runchal, thanks a lot for your great keynote. How do you see artificial intelligence helping in interpretation of CFD results, which is probably relating to what you just mentioned in your previous answer?
I think artificial intelligence, along with deep learning or data mining, whatever you call it today, there are all kind of things, I think will play a great role in two ways. One, people interacting with the CFD software in interacting with the engine, like a Siri kind of, if you're an Apple user or a Alexa kind of thing. So I think artificial intelligence will play a great role. I think the next generation of, if I was in a situation where developing a new code today, I will not be writing a GUI for it. I'll be writing a Siri for it, saying, hey, here is the geometry, pick it up from here, and here is the engine, and go find the property somewhere else. So I think artificial intelligence will be crucial to making CFD accessible. At the other end, the second problem is, how do we bring the results of the CFD to the notice of the decision makers? There was already a study of what would happen to New Orleans if a hurricane came. It was a multi-million-dollar study, but it said that you need to spend, I don't know, so many millions of dollars to make it safe. And the decision maker didn't understand that. So when the actual hurricane happened, they wound up spending billions of dollars rather than millions of dollars that could have been spent. So how do we convince the decision makers what is needed? And I'm staking my reputation and saying, if you do this, this will happen. So I think that is where the problem is. Then artificial intelligence would play a great role in will build up databases of both properties as well as the results. And then we will know what the reliability of the results is. We need to bound our results. I mean, if I'm an engineer, I need to say this thing would last for 50 years plus minus 10%, or this will result in this design, so those kind of decision making, only artificial intelligence can help us.
Thank you so much for that. Yeah, I think that's an important way or statement just to close this particular keynote speech. Thank you for that. Artificial intelligence informing decision makers, those are the non-experts in fluid dynamics. That ultimately is a very honorable goal to have. Akshai, thank you so much for speaking to us. It's been an absolute pleasure, an absolute privilege listening to you. And on behalf of everybody that's attending your talk, that has attended the talk, I'd like to thank you extremely, very sincerely and very much indeed. Thanks a lot. Okay.
Not at all. It's been my pleasure, and I love this field, and I love to talk about it. Thanks.
It's great that we've connected, and I'll look forward to catching up with you later on. Thanks again, Akshai. Okay. I'll move on to the next part of the presentation between now and the lunch break. If that's okay, I'll just go off camera and make a full mode presentation, if that's okay. So here we go. Manuel, if you just confirm we're back on full screen.
Yes, it is.
That's great. So the perspective of 50 years of CFD from Dr. Runchal, I think, has been extremely insightful. We're just going to make one or two steps in the context of OpenFOAM now to look forward to the next few years. This October, in fact, is marking the 3rd year of the initiation of the OpenFOAM Governance Steering Committee. So I just want to share with you a little bit of the background in terms of the structure, but also one or two of the key, let's say, successes that we've been able to achieve over the past 3 years. So the steering committee comprises the following kind of combinations of organizations. I act as permanent chair. But we have several OEMs and support organizations that are listed there. We also have representation for the release authorities, universities, and also the release and maintenance operation here at OpenCFD, represented by Andy Heather. So this is the team that is trying to establish and sustain the future of OpenFOAM for the needs of the future users, and incorporating everyone, that's including every one of you yourselves, contributing to the development of the code for the foreseeable future. So who informs the steering committee? There are a group of technical committees. The technical committees comprise 2 sets of groups. One is looking at the functionality of OpenFOAM, and one is looking at special interest application groups. So you can read it as well as I can on the screen. We have several functionality teams which are looking at the core capabilities of OpenFOAM. And then we have, for the moment, at least 3 special interest groups which are looking at applications. I'm extremely grateful to Professor Gavin Tabor for taking on the role of coordinating across the joint technical committees. And implicit in that statement is an appreciation to every one of you who is participating as a member of these technical committees. If you're not already doing so, please consider joining one or more and have your say in terms of where OpenFOAM can be going in the future in terms of functionality and applications, but also in the way that you'd like to inform the future governance and the decisions that would be made in general by the steering committee. My next slide is just talking about one of the successes here. You'll see another one in the next slides. And this one comes from the recommendation and the actions from the High Performance Computing Technical Committee that's chaired by Dr. Ivan Spiso. So from his efforts and the efforts of the committee and several other members, we have successfully bid for a project to be sponsored by the European Commission. The European Commission accepted the proposal in the middle of last year, and this particular project called ExaFOAM, which is deriving and commuting OpenFOAM towards high performance computing from where it probably lies at about 0.1 petascale towards exascale over the next 3 years. So the total project worth is around 5 million euros. I would say that the value of the technology which is going to be written into OpenFOAM in the next 3 years is about 2 million, and will include couple solver. It will include migrations towards GPU applications, optimization of HPC algorithms and architectures, and several of the additional points that you can see on the slide here. I'd like to thank all the participants of the main beneficiaries of the project, which are listed 1 to 12 on the right of your screen, but also non-beneficiaries of this particular project. These are organizations that are helping us to understand architectural constraints, offering advices, and also giving us an end user perspective with respect to how OpenFOAM will be used really in anger in industry. So thanks to all the participating organizations in this particular project, coming from the actions of the HPC Technical Committee. The last one I'd like to talk about is the initiative of the Documentation and Tutorials Committee. It's the formation of the OpenFOAM journal. It essentially has started this year. The first volume is just been published, and you'll be able to see the outcomes of the first journal publications in journal.openfoam.com. So please visit there. Currently under this platform, we have over 700 registered users of the platform. Many of you, over half of you, have volunteered to act as potential reviewers of submitted papers. The submitted papers work in review under a double-blind synopsis, so that means that the reviewers can't see the authors can't see the reviewers. So we hope this is going to be an enormous success with respect to publications around OpenFOAM of real high-caliber applications. The very unique part of this particular publication is that we intend to make available under each publication usable code, which is able to be downloaded and then used and validated against whatever cases are published within the publication. So I think with that, I'd like to go on to just advertise a few of the highlights from the next few days. You've just sat through the opening plenary. Thank you very much. We'll take a short break for lunch in a few minutes. After we return from lunch at 1 p.m. European time, we'll have a parallel session on transportation on the one hand, on multi-phase. So please read the agenda carefully, choose which presentations you'd like to be attending. Most of them will be pre-recorded presentations broadcast at the time advertised here on the screen. We'll take a short coffee break at around 3 o'clock at European time, and then reconvene at 3:30 with this new session, which is called Artificial Intelligence, and which will be a plenary session, so available as a single session to all the attendees. You'll see at about 5:30 CET that we're opening up once again the Meet the Experts session. I'm just going to list over here a number of experts within the OpenCFD and ESI environment. So please use your expert directly in Hopin to book your 10-minute slots with any of the persons that you see on the screen. Under their names will be a certain level of specialization that they're happy to admit to. I'm sure they're capable in many, many more items, but at least if you'd like to speak to them about the items under their names, then please book your 10-minute slot under your expert in Hopin. Incidentally, Hopin will also allow you to communicate with any other attendee on the conference. Manuela, straight after I finished in the next few minutes, will give you a quick navigation through Hopin in general. Let's look forward to tomorrow. Tomorrow we'll start at 10 o'clock CET. We'll be exploring some of the outcomes and the activities of the technical committees as a plenary session. So we'll be looking at the positive outcomes so far from the OpenFOAM journal, and also looking at the general tutorial collection, which is available under wiki.openfoam.com. And then we'll get an overview of the technical committees by Gavin Table himself. So thanks very much to Gavin for putting that together for us. Before the lunch break, we'll have the next parallel session on high-performance computing and the environment and health. Once again, please review the agenda very carefully. Even if you can't make at the advertised time any of the presentations because you happen to be watching the parallel one, all the presentations will be available as a recording for you to observe or listen to after the conference or even during the conference. After the lunch break tomorrow, we'll have another parallel session on heat transfer and environmental and health. And then towards the end of the day, we'll close with a plenary session, hopefully closing with a big bang. And that's an open panel discussion session chaired by Gavin Tabor, involving any questions that you might like to ask or general discussion among the technical committee chairs. We'll finish with our second keynote. The second keynote will be presented by Philippe Spanart. Needs absolutely no introduction in terms of his impact and contribution to turbulence modeling and turbulence research for the past several decades. And that will take us to the end of the conference. So I think with that, I'd like to just advertise some activities on day 3, which is the 21st of October. In the morning, there will be some paid trainings and workshops as we've normally offered, usually in terms of best practices and meshing practices in OpenFOAM, and a parallel session, short training on the use of the adjoint optimization methodology within OpenFOAM release version, the latest, which is version 21.06. In the afternoon, there will be 2 free workshops, again in parallel sessions. The first one for anybody that'd like to explore a GUI environment for OpenFOAM, and the second is beginning to look at the lessons learned from COVID-19 pandemic in terms of how we're going to go forward. Avoiding the next pandemic or the impacts of the next pandemic, but in general to learn about the air quality for especially indoor environments to allow us to lead better, healthier, and less impacted by viruses activities. Okay, and with that, I think that's the last you'll hear from me from this morning. Perhaps now I can pass back on to Manuela, who will give you a quick navigation through the Hopin platform so that you make absolutely the best of the sessions for this conference over the next 2 days. So Manuela, thanks so much. Back over to you.